vortex dynamics broadly. And also we start to think about doing thermal transport as well in order to probe this problem. In fact, I don't know, this wasn't exactly your question, but I could also mention, so in some sense, one of the disappointing things about, or not, maybe that's too harsh a statement, because we don't see any simple linear extrapolation. And going back to Jean-Marc's question, this is independent of any criterion we use. Okay. I didn't explain where this bound is coming from. This bound is coming from by putting the magnetic field in the plane. You know, where do we see vortex kind of dissipation? You know, basically on the statement that if this is properly identified by us, that this is vortex transport, you know, what we see is very analogous to the cuprates. That gives you kind of a bound that down to this thickness that if we see vortex dissipation, then it must be small enough to put in a vortex. So that's kind of the weak bound we have for superconductivity in this regime. As far as the other direction, I absolutely agree with you. Unfortunately, we don't have a clean experimental knob to tune yet, in the sense that, as you say, that the density of our defects is on the kind of few nanometer scale, and in fact, the mean free, the transport coherence length is also very small on that scale, and so to most satisfactorily answer your question, it'd be lovely to compare that with essentially with the clean, much cleaner sample. The thermodynamic superconducting coherence length we expect is an order of magnitude, more than an order of magnitude larger. So we think that we're being brought down very, very hard into the dirty limit by the transport mean free path. But similarly, you know, we could be in a very different regime. And I think your caveat is well taken, that I was advertising that our critical current density is comparable to cuprates. But that's in some sense not a fair comparison, because that statement is for our, let's say, dirty samples in some language with lots of vortex pinning centers compared to, you know, clean cuprates. And if I play the same game in the cuprates that people do, you can go up past a megaamp per centimeter squared. So that's a very good point.
Okay, sorry, folks. And all of a sudden, we lost power in the neighborhood. And so for 5 minutes, I don't know what happened. So we got power again. And so I'm resuming the moderating role. Sorry. So I missed a bit of the action, but so any more questions?
So I asked a question. I typed a question about the magnetic resistance. So I saw when you show the magnetic resistance being negative and boring, there was one composition where it looked positive at 10 Kelvin, 0.225. Is that correct?
No, it was, sorry, I don't know what's wrong with my, so yeah, sorry, this is the superconducting transition. So this,
okay.
So
I got it. Mm-hmm.
Yeah, so at 10, this is kind of our highest, near the highest TC sample, and so this is it's a suppression to superconductivity.
Right. Okay. And do you have anything to comment about the nature of the pairing?
I want to very much, but as an experimentalist, basically no. I'm not trying to be disagreeable. It's just that we don't have any experimental statement we can make at this point. As I said, that most of the theory people would say, using some sort of electronic instability, that it must be x squared minus y squared. I I should mention that there's a paper on ConMat from Nanjing claiming by tunneling spectroscopy things that look like either a D or S wave gap. I don't really know anything about their work to put that in context, but I can say that certainly there is in the last month both theory and experiment discussing these sorts of spectroscopies. But in our own work, right now we can't say anything useful, I'm sorry to say, but we'd like to.
Okay.
Yeah, I'm sorry, maybe this was too early to give this kind of a talk because most of my answers are, I don't know. But anyway, hopefully that's why it'll be fun to keep working on.
Thank you.
Any additional questions? No, so everybody's exhausted. TGIF. But no, so it was a great pleasure. And I think it was very much to the point to end this this school with Harold's presentation. It was very nice and clear. I hear whisper, so maybe somebody has a question, but looks in Jean-Marc's group.
No, Mark. We were just switching on the camera to be able to thank Harold and later to thank you.
Okay, so indeed, let's thank Harold once again very much. And I agree with you. I mean, it's too bad that we couldn't make it in Les Houches. And I hope that in the future we'll have further opportunities to correct that.
Yeah, very much. Yeah. Thank you for organizing. I appreciate it. Appreciate the opportunity. And
for the occasion, of course.
And thank you, Mark, for all the work you've been putting in the school. It's been, I know, a really tremendous work. So thank you very much.
Thank you, Jean-Marc. My pleasure. Okay, so everybody, thank you for being with us until the end of this session. And I guess until we meet again, I mean, I don't know when. We were supposed to be at Stanford, but obviously we're in Paris.
Yeah. It was great to see lots of friends, and everybody stay safe. I hope to see you again soon somewhere, either here or there.
And say hi to Tia. Okay.
Yeah, we'll do.
Bye.
Bye.
Bye.